Test, test, 1, 2. There we go. Good evening, everyone. Welcome to Science Café. It's a lovely evening here in Tucson, Arizona. It's a great evening to learn about the moons of Jupiter as part of our Moons of the Solar System series. My name is Shipard Reed, and for those of you who haven't been here before, I work at the Flandreau Science Center and Planetarium. We have some great new shows. We have an amazing black holes show in the Planetarium Theater, so if you haven't come and seen us lately, come visit. We've got great exhibits. We have the U of A Mineral Museum, which is a dazzling collection. And we also encourage you to visit all the other UA Science outreach sites. That includes Biosphere 2, Tuamac Hill, the Mirror Lab, the Tree Ring Lab, and Flandreau Science Center and Planetarium. This evening, we're very pleased to have Professor Alfred McEwen from the U of A Lunar and Planetary Lab. Please give him a warm welcome, and let's learn about the moons of Jupiter.
Can you hear me? Yes. All right. I'm going to talk about Io and Europa, two really amazing moons of Jupiter. So first, to put this in perspective, there are lots of moons in the outer solar system. Let's see, this is on Facebook, so I'm supposed to be about here. All right. Then I'm blocking the screen, aren't I? We have 4 giant planets in the outer solar system: Jupiter, Saturn, Uranus, and Neptune. Jupiter has 67 moons, but 4 big ones, planet-sized moons. Saturn has 62 moons with 1 big one, Titan. Both Ganymede and Titan are bigger than the planet Mercury, so these are substantial moons. Then Uranus has some mid-sized moons. Triton has 1 fairly large moon, bigger still than the planet of Pluto that's down the bottom there. And you can see Earth's moon for comparison is about the same size as Io and Europa. Io is a little bit bigger, and Europa is a little bit smaller than Earth's moon. So some of you may be used to the terrestrial planets, Earth, Venus, Mars, Mercury, and the life cycle of terrestrial planets is kind of boring. It's like the Western concept of human life. You're born, you're young and energetic, then you slow down, and then you die. Boring. The outer planet satellites are more like the Hindu concept of reincarnation, because there's orbital evolution and tidal heating, and they can go through cycles of activity and quiescence and a high heat flow and activity throughout their lives. So these are very bizarre worlds compared to the inner solar system. Right, so Jupiter has 4 large moons. From inner to outward is Io, Europa, Ganymede, and Callisto. And these are shown to scale with each other and against massive Jupiter. Jupiter is enormous, and that gravity has a big effect on what's going on here. So the inner 3 moons, Io, Europa, and Ganymede, have this very strange orbital resonance, where every time Ganymede goes around once, Europa goes around twice, and Io goes around 4 times. And so if you watch this, you see them periodically line up. There, they're lined up. There, they're lined up. And when they line up like that, it creates a gravitational pull on the orbits, especially of Io and Europa, so that the orbits, instead of being circular, they'd want to evolve into a circular orbit over time, but because of this strange orbital resonance, they're kept permanently in this eccentric orbit. So what that means is they're sometimes closer to Jupiter, sometimes further away. And Jupiter is so massive, it deforms the whole satellite. So it changes its shape. And Io's orbit is only about 2 days, and Europa is about 3 or 4 days long. So on a rapid time scale, these satellites are changing their shape with the orbit. And that's what causes the tidal heating. It's like bending a piece of metal back and forth. It gets warmer. So this creates the intense tidal heating, especially of Io, but also Europa, and even Ganymede probably in the past more than today. And tidal heating is a heat source that was pretty much not recognized in the inner solar system. In fact, there was a little bit of it at times, but it's a major heat source elsewhere, like exoplanets and for many other satellite systems. So the orbits and tidal heat of Europa, Ganymede, and Io are linked. So it's the orbital speed and the resonance that varies. It may vary periodically over time. This shows some models. The top is eccentricity versus time. The bottom is heat production versus time. And the eccentricity, Europa's at the top. It actually has a more eccentric orbit than Io. But Io is closer to Jupiter, so it experiences the greatest deformation in tidal heating. So on Io, we have volcanic hotspots that are so hot we can measure the heat flow and get an estimate of the tidal heating in that manner. But then for what is Europa's heat flow, that's a topic of great interest. We can estimate that from Io's heat flow and such models as this. And these models, some of these models predict this periodic tidal heating. I hope you're not getting too drunk. It's not you from too much beer, it's the screen. But if it is, episodic like this, where are we now? And if it's episodic on Io, it's episodic on Europa. So where is Europa now? Is it in a quiescent state, an active state? So there's something else really bizarre about the Jupiter system, and that is Jupiter has the most powerful planetary magnetosphere in the solar system by far, and it's tilted 10 degrees, so it doesn't rotate with the planet. It has different rotation, and this is decametric radio emissions as viewed from Earth. But what happens is, from the satellite's point of view, is this magnetic field is sweeping up and down over time rapidly. It's like a 10-hour, well, it's about 12 or 13-hour period, because Io and Europa are moving in the same direction as Jupiter's magnetosphere. But what this does is the magnetic field moving up and down, and it's like an electromagnetic probing of the interior. And the magnetic fields change if there's a conductive material in the interior. And it does change as if there's global conductive material inside both satellites. And that's believed to be salty water inside Europa and magma, liquid rock inside of Io. All right, if you've been to Las Vegas, you know their slogan, well, what happens on Io doesn't stay on Io. Plume material from Io has volcanic plumes up to 300 kilometers high, even maybe 500 kilometers high, lots of them. This material ejects particles, mostly sulfur and oxygen, into Jupiter's massive magnetosphere, and this then gets wrapped up, it gets charged up by the magnetosphere, and when it's charged up, then it moves with the magnetosphere and creates this plasma torus around Io's orbit, but the plasma torus extends out even to Europa, and so this material from Io is impacting Europa. And this may actually be planting material that's important to hypotheses about life on Europa. It also causes aurorae on Jupiter. And okay, so let's talk about Io a little bit. This is a nice full disk image of Io from the Galileo spacecraft mission. And you see all those dark spots? Most of Io is covered by SO2 frost, which is bright, or other sulfurous material that may be reddish or orange and so forth. Those dark spots are where there's no such SO2 frost. Why? Those are all hot spots. Those are all exposed silicate lava that has erupted so recently that it's still hot and the SO2 can't condense on it. And there are hundreds of these hot spots on Io, and these are intensively active volcanoes. A volcano like Kilauea, typically the most active volcano on Earth, is so small you wouldn't even see it here at this scale. So this is volcanic wonderland. One of my favorite spots is Pele's plume. We first saw this from the Voyager flyby, which was in 1979, and it took this series of images that was in oblique view, and back 30 years ago, I processed these images, mosaic the black and white images, and merged it with a color image, and then there's a plume there that stretched it separately, so you can see it, it's really faint, but the eruption of Pele starts from right there, the little dark spot there, and then it makes this big plume, it makes this dark region as the fallout region. It covers an area the size of Texas, and then we're looking obliquely through the plume to see this complicated structure in the plume up there. And Io has other interesting things like mountains. Here's one that's that's actually the tallest mountain on Io, about 18 kilometers. And how those form is another interesting story. At bottom are 3 images of Pele from the Galileo spacecraft. It makes this big red ring. But then another volcano erupted here called Patera, which was a short-lived outburst. The astronomers tracked these outbursts. But it was short-lived, and then over time, the Pele plume is reasserting itself. So here's a plot of Io's enormous heat flow, and this is in watts per meter squared, how much energy per square meter on average is coming out. You can see the moon is almost nothing. Earth today is somewhat 10 times, 20 times more than the moon. Hadean Earth, around 4 billion years ago, was quite a bit higher. And, you know, Europa today may be somewhere between Earth today and Hadean Earth. But there's Io. It's a good order of magnitude or more higher than Hadean Earth even, or Europa. So the eruptions on Io make these enormous lava fields. And this shows in black the Emirani Maui flow field. This is the largest currently active flow field in the solar system. There's hot spots at various places. We know it's active. Then for comparison, here's the longest currently active lava flow on Earth, the Upwelling flow field from Hawaii, that little thing there. Here's the longest lava flow observed by human beings, the Laki, 1783 to 84 Laki flow in Iceland. But there were big lava flows on Earth in the past. The most recent one is shown here, the 10 million year old Pomona flow field up in Washington. So the effusion rates, we can categorize the eruption style. The effusion rates are 10 to 100 times greater on Io today than comparable eruption styles on Earth. But there's also eruption styles that we've never seen active on Earth. There's so much energy and such a high eruption rate, but it happened in Earth's past, and I'll get to that later. But in any event, Io allows us to directly observe. This happened in the past on the other terrestrial planets. The Moon, Mercury, Venus, Mars, all have these ancient giant lava flows. The only place where we can watch it happen today is at Io. And one of the things that we really want to know is the temperature of the lava, because that tells you about its composition, the state of the mantle. And we thought we measured some especially surprisingly high temperatures from the Galileo mission that suggest lava that's especially enriched in magnesium, ultramafic lava. It gives it a very low viscosity, and it's runny almost like water. And it implies a very high melt fraction of the mantle, so that's consistent with having a magma ocean in the mantle, if you will. It's probably interconnected magma. But the Galileo data was poor. The instruments were not designed to measure this, so we need to go back and do this the right way. And the problem is that you're up lava, and it immediately starts cooling, it spreads out, and you have this whole range of temperatures. And remotely you measure this mix of temperatures, and really pulling out the peak temperature is hard. But what we need to find are skylights. So there are these lava tube skylights in Hawaii, and that's molten lava there, and then all around the outside it's cooled. It's the ambient temperature. So you have this, you don't have those intermediate temperatures unless it's a big skylight and there's reflections off the wall and so forth. So we think that there are this kind of insulated lavas on Io and that these probably exist. So we hope to do this in a future mission. In fact, the Europa Clipper mission that I'm talking about may be able to do this for Io, even though it doesn't come close to Io. Now I'm going to switch to Europa. And Europa may have all the ingredients needed for life. It has lots of water, as indicated by the magnetometer data in the subsurface. It may be rather deep, tens of kilometers deep. There may be pockets, as shown in the upper right there, of water that can help to explain some of the chaotic terrain we see on Europa. We see this red material that erupts along fissures and maybe eruptions from the ocean, and we want to know the composition of that. And for life on Europa, it's not going to be photosynthesis. It's 5 times further from the sun, which makes the sun 25 times weaker than an Earth. But it's also beneath all this ice, so it needs a different source of energy, such as chemical disequilibrium. And so we see on the seafloor, we see these black smokers with this whole ecosystem that lives off of the chemical energy that may exist on Europa from the tidal heating of the silicates at the base of the water. And there's other ways of creating this chemical disequilibrium, such as Io dumping material at the surface of Europa, which might get into the subsurface. Europa may have a form of plate tectonics. It's not exactly plate tectonics, but here's a little animated GIF where it's just one image, but you can, that's the original image, but then you can reconstruct the way it was before, and the features line up that didn't line up before. So we're sure this has happened, spreading centers. There are large transformed faults. There's an example of one that's about the same size as the San Andreas fault. The chaos terrain is a little different. There are some low amplitude folding seen. There's also places that I didn't illustrate here where it looks like a piece of ice shell went underneath another ice shell, which is sort of like subduction in plate tectonics. It's not exactly like Earth plate tectonics, but something equally interesting. So we now have a mission in development to Europa called Europa Clipper, planned to be launched in 2022. And the science community has tried for 20 years to get NASA to approve a new mission to Europa. Ever since we got these Galileo results, we've been arguing for this. It keeps getting put off. But there is a congressman from Texas, John Culberson, who's a Tea Party Republican. He loves Europa. And he's chair of the House Subcommittee on Commerce, Justice, and Science. And every year he has been giving NASA extra money for Europa that they didn't ask for. Here, take an extra $100 million anyhow, do studies. Pretty soon NASA gave in and said, okay, we'll start a new mission. And it's really thanks to him that we have this mission. The goals of this objective are to explore Europa, investigate its habitability, including the ice shell and ocean, including any ocean surface interchange in particular, understand the composition of the surface, especially those materials that may have erupted from the ocean. The geology, understand the formation of surface features, especially the sites of recent or current activity, which is cool, but also very relevant to the search of life on Europa that I'll describe. The Europa Clipper has 9 science instruments and a couple of other science investigations using instruments. I won't attempt to describe all of these to you. It's very comprehensive. But I'm involved with the Europa imaging system, ICE. That's German for ice. It's also German for ice cream. So we can eat ice cream at all of our meetings and justify it. But I'm the deputy PI of that experiment. The PI is Elizabeth Turtle, goes by Zibby, and she's a former graduate of the LPL, University of Arizona. And so the previous best image of Europa's surface from Galileo was one tiny little area at about 6 meters per pixel scale, the piece of it at the upper right there. Well, what we can get is 0.5 meter per pixel scale. And here's an example of part of the Antarctica ice shelf at 0.5 meter per pixel to give you a preview of what we'll be able to see on Europa. The shadows won't be so bright on Europa, but so also in in planning, formulation, or whatever you call it, is a Europa Lander mission. And this is controversial because it's expensive. It's really hard to land on Europa. You need to launch mostly a bunch of fuel, first to get off of Earth, then to be captured by Jupiter, then to be captured or slow down close enough to Europa to land. But one thing I haven't mentioned, all of these cartoons I show you of Europa, they show a plume going off in the distance. We haven't actually confirmed that there are plume eruptions on Europa. We know there are on Io, we know there are in Enceladus, a little moon of Saturn. The Hubble Space Telescope has detected something along the limb that has been interpreted as plumes. They don't quite make sense to us because they're too big for water ice plumes, but there may be plumes on Europa, and that has made a big difference in planning for future missions. So the artwork all shows them anyhow. So Europa Lander has ambitious science objectives to search for life, actually search for life. We haven't done that since the Viking landers 40 years ago. We've had missions that investigate habitability, which means look for water and things like that. Actually trying to detect life is something NASA has not done for a very long time, as well as further understand habitability, the geologic context, and support for future exploration. They've proposed a straw man set of 5 instruments, not necessarily what would actually happen. But there's a couple of big challenges for this Europa Lander. One is that we don't know what the surface is like at high resolution at the scale of the lander, which is about a meter or 2. Ice-rich terrains on Earth are often really bizarre, really rough, sort of like this artist painting. And the engineering challenge of landing on a surface like that is large, so you'd rather land on a flatter surface for sure. And that's not all. They also really want to land near a site of very recent activity. Some upwelling from the ocean, either next to a plume or some other sort of activity. This cartoon illustrates some ways in which ocean water may erupt to the surface. But the reason for this is that Io is bathed in this very intense radiation because of Io throwing all the stuff out. The plumes that get charged up and deposited, mostly energetic electrons, and that breaks down organic material very rapidly. So you can't really search for life if the organic material has all been broken down into smaller chains of organics that you can't really identify and understand. So the goal here is to find not only a safe landing site, but next to one of these active sites. So this will be quite a challenge for the Europa Clipper mission, but it'll make it fun to have that challenge to try to find that site. And then sometime in the future, we'd really like a submarine to go down and look at the seafloor. And I think this is supposed to be a black smoker hydrothermal vent. It kind of looks like a life form. You know. Okay, so who cares? Well, besides Io and Europa being amazing worlds, why do we care? So I'm going to start off with a little quiz. What killed the dinosaurs? Was it galactic cosmic rays from a supernova? Was it a giant asteroid impact? Was it voluminous volcanism? How many people think galactic cosmic rays? How many think asteroid impact? Okay, how many think lots of volcanism? A few, okay? Pretty much 100% of the public is now convinced that it's asteroid impact. But the real story is not quite that simple. There was a study about mass extinctions focusing on volcanism and impacts with multiple authors, and the book came out here. And they've concluded, first of all, there have been 5 mass extinctions in the Phanerozoic. That's the last 540 million years. Phanerozoic means visible life. If there were mass extinctions before that, we wouldn't know how to recognize them. But the cause of at least 4 out of the 5 of these has been ocean acidification resulting in a carbonate crisis. You can't make carbonate anymore as a primary cause. And this ocean acidification was caused by voluminous volcanism. Very voluminous volcanism, like that happening only on Io today. And by the way, some workers suggest that we're now entering a sixth mass extinction, although it's not from volcanism, it's from us. But the same kind of sort of chemistry, acidification of the ocean. So what happened at the end Cretaceous mass extinction, that's what killed off the dinosaurs. The Chicxulub impact happened at about the same time as the massive volcanic eruptions on India and this mass extinction. And the old view was that these lavas in India, called the Deccan Traps, erupted gradually over 5 million years. So how does that cause a sudden mass extinction? But newer age dating has showed, in fact, there was this very strong pulse. 80% of it erupted just before this mass extinction. And so the new view is that a single large asteroid impact could not have been the sole cause of this mass extinction, particularly in the ocean, but the dinosaurs were on land, but rather was a contributing factor. This is still a raging controversy, but my point is a reason to study Io. I want a reason to study Io. So we want to study how these high rate volcanism occurs. That's the only place to go to study that. And also to understand how ocean chemistry changes. Why not go study another ocean, like Europa's ocean? And by the way, there might be life there. That's cool too. So I'll take as many questions as you can stand to ask me. To wait for the mic.
Yes, there we go. Just to review, I know a lot of you have been here before, but if you haven't been here before, the way we work our question and answers is if you can raise your hand, I'll bring the microphone to you so that everyone can hear the question that you're asking. And if you don't feel comfortable talking on the microphone, you can tell me your question and I'll ask it for you. And I will get to people in the order that I see hands go up, and I'll do my very best to get to everybody. I saw a hand go up right here right away, it seemed like, so I'm going to go there first.
Okay, hi, thanks. It was a great talk. So there are a lot of moons, I gather. You originally said it was 67. And I kept reading 69, and then there's this whole group that they don't know if exists or have names or whatever. Can you kind of comment on that end that's kind of this unknown and what the real number really means?
Right. Well, I haven't really kept up with this. I don't remember hearing about new discoveries recently. Maybe it's 69 instead of 67. Most of these are floating rocks. They're small bodies, and they're far away from Jupiter, and many of them may be captured objects, probably comet-like materials from the outer solar system, and they're interesting for other reasons. But there's a lot of them. They're small, and it's hard to find. There's probably more. We just haven't found all of them yet, but there's a lot of them.
Thank you. And now we have another question over here.
What is the chemical composition of the ice and water that you can observe from satellite imaging and so on?
Okay, well, from satellite imaging, we don't measure composition that much from sort of visible wavelength imaging. We depend more on things like a near-IR spectrometer. And Galileo had one of these. Europa Clipper will have a better one. And so ices have very pronounced absorption bands. Water ice has big, deep absorptions, and it's very easy to identify. And salts have different absorption bands. Salt combined with water have still different absorption bands. Those are some of the materials suspected to exist on Europa. Methane and other volatiles as frost or ice have very different bands. So that's how we can tell from remote sensing. There's also hope of being able to identify organic materials from remote sensing. Those have much weaker absorption, and it's often a 3-micron region where, because of the water ice in Europa, it's black, so it's very low signal. So that's a big challenge. And this is one of the arguments for a lander. To really understand the composition, you need to get down on the surface and put it into a mass spectrometer or something like that to really tease that out. But we can tell a lot of things from remote sensing anyhow.
Thank you. There's another one right up here.
At the beginning, can you hear me? At the beginning of your presentation, you identified 4 moons, but you didn't say anything about that 4th one. I was wondering how it rotated and
Oh
and
yeah,
what the story is.
poor neglected Callisto. That's the outermost moon. It doesn't have the same resonance, so it's not part of this tidal heating scenario, and it hasn't experienced any tidal heating. So it's old surface, many impact craters. It's been beat up. It hasn't had the kind of internal activity of the other three satellites, which you can say is boring, but then again, it's like the control experiment. You know, here's what happens to a satellite in this system that doesn't have tidal heating. And also, from the magnetometer data, there's also evidence for salty water in its interior. It's probably much deeper, and it's not as interesting for life for various reasons as Europa, but we shouldn't ignore it. You're right. Callisto.
Thank you. Oh, there's another one. Coming to you.
I just wanted to plug your new book, Mars. Thank you, thank you.
U of A Press.
Can you tell us what that's about a little bit?
Sure. It's called Mars, the Pristine Beauty of the Red Planet. I'm the PI of the HiRISE camera that's been orbiting Mars for 11 years now. We take highest resolution images of Mars, and we put together a book of our favorite, most beautiful color pictures with captions, and it's heavy. Make sure you get your insurance up to date before you pick one up. But U of A Press published that this past spring.
I will add, having seen the book, that the imagery is absolutely stunning from the HiRISE camera that orbits Mars. And those of you who can make it over to Flandreau, we have a gallery of images printed out in very high resolution that are quite captivating on display right now. So I encourage you to check out the book and the exhibit of HiRISE photos at Flandreau.
I want to make those kind of books for Io and Europa now in the future.
Here's another question right here.
I just wanted to clarify, so the Europa Clipper will actually be visiting both Europa and Io?
No, it orbits Jupiter, making a series of close passes just to Europa, a few close passes to Ganymede and Callisto in part to help phasing of the orbits. They don't want to ever make a close pass to Io because of the intense radiation there. However, from the orbit of Europa, the ice narrowing camera can get images about 1 kilometer per pixel. And these hot spots from a skylight are so intense that we can detect it even when it's very smaller, much smaller than the pixel scale. So we have hope of being able to measure temperatures of the lava in spite of not getting that close. I think I am hoping to propose a new mission that does make flybys close to Io. But we'll see.
We have some questions back here.
A quick follow-up to that, then my question. The follow-up is, so the Europa Clipper will not go into orbit around Europa, around the planet.
No.
And then tell us about the timeline for Clipper. I know you're working on the instrumentation now.
Okay. Yeah, it's there was a concept for a Europa orbiter. The problem is when you're in Europa orbit, you're always getting this high radiation dose, and that limits the lifetime of the mission. So what they're doing instead is orbiting Jupiter. Most of the time they're far enough away where the radiation isn't very high. They whiz by Jupiter, by Europa quickly, and that way the mission can really collect a lot more data over its lifetime. So the status of the mission is it's an approved mission. Instrument development is underway. The plan is to be ready to launch by 2022, but that's on the Space Launch System. I don't know how many of you are familiar with that. That doesn't exist yet. It's a big new launch system that's designed for human exploration. And it was recently announced that the first launch was delayed. And so I'm concerned that it won't be ready to launch the Europa Clipper in 2022, and it'll be delayed. The advantage of Europa Clipper is that it gets you there fast in just 2.5 years. We could also go by an existing launch vehicle, but it needs to get gravity assist from Earth and Venus, and it takes 7 years to get there. So, you know, I'd like to get there sooner myself. So we hope that the SLS will be ready and actually launch this mission, but that's the uncertainty.
So with one of the Clipper's mission priorities be to find that landing site for that potential Europa Lander?
Absolutely. That would be the top priority, really, to NASA, and that'll be in conflict with the science priorities that we carefully work out, probably, but that makes it fun to have some controversy. And yeah, absolutely. And there's not just the imaging, it's also other instruments that can detect current activity in particular, and instruments that tell us about the radiation environment of the surface, because that plays in. We need to learn as much as we can about Europa to pick the best landing site.
There's one right here, and then I'll get over to you.
I'm not certain if I heard you say the expected length of time it will take for the explorer to get from Earth to where you're looking for it to go around Europa, Io.
Right, so for Europa Clipper mission, if it's on the Space Launch System, it gets there in just 2.5 years. So launch in 22, it'll arrive in 2025. That's actually within sight, I guess. But if there's delays in that launch vehicle, if it's a different launch vehicle, it can take longer. So we don't know. And that only goes to Europa. Mission to Io, I hope gets accepted, but it hasn't happened yet. Who knows when that'll happen? It's a hope.
Okay, I have another question. Has there been any kind of material detected anywhere in space that is unlike something on planet Earth?
Any material in space unlike, well, there's plasma. That's a state of material that's extremely hot, like the atmosphere of the sun. We fortunately don't have that on Earth except in the H-bomb. As far as like minerals, there was some minerals, a few minerals discovered on the moon that were unique from moon rocks. Although maybe there was Armstrongite, named after Neil Armstrong. I think that was discovered on Earth later. It just hadn't been known at the time. I don't remember exactly. So there's a few things like that. But I mean, there aren't new elements. I think we know all of the elements, but different minerals and different states of matter, yes. But they're also, I mean, just to go even further, deep in these giant satellites under extremely high pressure, you can turn hydrogen into a solid, like a diamond. You can't do that on Earth.
Right here.
What is the expected life cycle of the Clipper? And during that time frame, who will be managing the control project manager experience?
The life cycle for the mission, the Europa Clipper mission?
Yeah, how long do you expect it to last once it gets there?
Right, okay. So the nominal mission is 4 years, with something like 45 flybys of Europa. But typically things are intentionally over-designed. They want lots of margin to guarantee success. And so there's a radiation design margin of 2, for example. So if you believe that literally, it means we could last twice as long. The Galileo spacecraft actually lasted 4 times as long as its design lifetime, although lots of things failed along the way, and it got more and more, challenging to make things work. But so we'll get some extra years.
And we've got another question here.
For a mission to Io or another one, how do you go about hardening it against radiation, the probe?
Right, so there's 3 ways to harden against radiation. One is to minimize the radiation dose. So for Io, the mission concept is to fly by even faster, so to minimize the time in which you're receiving that radiation dose, to minimize the first place. The second way is shielding, and the Juno spacecraft, the orbiting Jupiter, has a vault with thick metal, titanium shielding all around the end of it that stops most of the energetic particles, although there are secondary particles and complications. And the third way is to have electronics that are intrinsically radiation hardened, and those exist increasingly. So a combination of those 3 methods. We can harden spacecraft a lot better than we can harden human beings. That's a real challenge.
And, oh, another one back here.
If you had a cage match in the search for life, Europa and Enceladus, what's your bet?
Wow. Some people would add Mars to that, but okay. There's different arguments about this. Enceladus, we have measurements from the Cassini spacecraft that tell us certain things that we don't know about Europa. First, we know there are plumes, but from those plumes, we know that there is the kind of chemistry that could support life. There's an excess hydrogen, for example, that's a source of energy for life. So that, and we know that there's organic material. We don't know what kind of organic material, but we know there's organic material in those plumes. We don't know those things about Europa. On the downside, Europa is a small satellite, and so it's hard to understand how it could have enough tidal heating to have maintained this activity over geologic time. It may be only recently active. So if it's only recently that it's created habitable environments, it's less likely to be inhabited in spite of being inhabitable. Whereas Europa, with this, it's probably had a longer history of tidal heating, it's a bigger satellite, and so it's more likely to have long-lived habitable conditions. So these are debates. Nobody knows the answer. I don't have a favorite. I think we should explore both.
All right, we've got another question up here.
Hi, could you tell us how you became interested in astronomy initially? Did you want to be an astronaut? And then how, what about Jupiter in particular?
So I grew up as a teenager during the Apollo missions. A lot of my colleagues in planetary sciences saw that, wanted to be astronauts, and then planetary science became like a consolation prize. I never really wanted to be an astronaut. I was more inspired by the pictures of Earth in space and wanted to be an environmental scientist, and that's what I started off as. But then I just moved to Flagstaff, Arizona for a second career, going back to school, and there was the Center for Astrogeology at USGS up there. I needed a job. They said, okay, we can hire you to study the Galilean satellites. And later I asked a friend of mine, what are the Galilean satellites? So I just sort of stumbled into it and really liked it and stuck with it. It wasn't the plan.
That's a great path to planetary science. Do we have other? There's one up front there. Coming to you.
Other than the 4 primary moons of Jupiter, all those other moons, are they just hunks of dead rock, or are any of them very interesting, or is it really very well known?
Well, they're much smaller. They're not geologically active in the same sense as Io, Europa, and Ganymede, but they're interesting in other ways. They're very small bodies. They have irregular, odd shapes to them. Some of them are very primitive, and so for people interested in understanding the origin of water in the solar system, for example, one of those primitive bodies is an attractive target to understand. It's like a comet, and so and they also can tell us about the whole history of the solar system. We used to think the solar system was this calm, systematic thing. Now we understand that the giant planets have migrated over time. These have kicked out the asteroids and comets and created all sorts of havoc across the solar system. But what exactly happened when is still not fully understood. But by studying some of these small bodies around Jupiter, we can understand that history. And there's actually a mission now, a discovery mission called Lucy. Like I love Lucy, but it's to study the Trojan asteroids of Jupiter. So there are 2 Trojan points, stable points, and it's co-orbital with Jupiter. They're not satellites of Jupiter, but co-orbital. And they may be captured Kuiper Belt objects, or they may be something Kuiper Belt is the belt of material further out in the solar system, like Pluto, or they may have some other origin. So that mission is designed to study this type of small body. So that's of interest to Some people, I prefer Io. I want volcanoes.
Coming to you over here.
I couldn't resist. So your last slide, your smiley face, looks like gravitational lensing. Where is that? What is that?
Yeah, that's gravitational lensing. That's an HST image. It happens to make a smiling face, and I can't tell you where it is. You can probably look it up.
Can you help the rest of us understand what is gravitational lensing?
Okay, so this is Einstein's theory. I'm totally out of my depth here. But Einstein's theory is that a massive object warps space-time, and so if you have a massive object, the light waves get bent around it, and that can make a sort of lens that you can see something magnified that's at much greater distance. So don't ask me to explain it any more than that, please.
That's helpful, though. That's helpful. Just the concept. Do we have any looking for hands? And I'm missing right here. Another question? So the question is, do you have a pet named Io?
I do not, but my former boss and great friend and faculty and scientific mentor at the USGS, Larry Soderblom, he had a dog named Loki after one of the volcanoes on Io.
That's almost. Any other questions? Oh, right here.
So assuming the lander mission occurs on Europa, since Europa is tidally locked, if you land on the opposite side, does the magnetic radiation from Jupiter extend there?
Yeah, so where you land, it is tidally locked, so one face always faces Jupiter, just like Earth's moon faces Earth, and where you land matters, but it's actually the trailing hemisphere in the orbit that gets bombarded because Jupiter is rotating much faster than the orbital speed, so it bombards the trailing hemisphere with radiation preferentially. And there's also very high energy particles that, for reasons I don't quite understand, bombard the leading hemisphere. So it's probably, really it's the polar regions that are probably the most protected, strangely enough.
Thank you. And once again, any other hands going up? I don't see any other hands going up, so I get to ask a few questions for once. I'm sure there are theories about how these large objects that contain lots of water formed. Could you share those with us?
So how did the Galilean satellites form, for example?
Yes.
Well, there's a very interesting theory by Robin Knupp and co-authors that as Jupiter was forming, it was sucking in material from the protoplanetary disk, gas and mostly gas, but then water is a little bit less volatile. But it forms a whole series of satellites, which then get sucked into Jupiter's interior. So by that theory, there were a whole bunch of other satellites that formed, then got destroyed, eaten by Jupiter, and these four are just the survivors at the end of the process. But the other interesting thing is that there's a gradient in Jupiter where Io is mostly rocky. It doesn't have water ice. Maybe it had some and lost it over time, but it's mostly rocky with an iron core, a dense object. It's denser than Earth's moon even. Europa has got a nice shell, but then it's mostly silicate, so it's still pretty dense. Ganymede has about 50-50 ice silicate. Callisto is mostly ice. So there's this gradient, compositional gradient, that's sort of like a mini solar system. So there could have been a temperature gradient that influenced how different materials condensed, sort of like a mini solar system around Jupiter. But this is all subject to extensive debate.
But it's interesting. Thanks. And then there's so much exciting planetary science going on these days. Outside of the Galileo moons, what are some particular areas of investigation or discoveries that particularly excite you?
Well, the Cassini mission just ended, but we're still analyzing the data. But that was amazing. Titan, I didn't talk at all about that. You know, liquid methane and ethane seas at the polar regions. It's got a thick atmosphere with a cycle of rainfall, methane rain, carving channels. There's Enceladus that we did touch on briefly. Mars, I can talk about at great length. It's still an interesting world, especially for ancient Mars when it was more Earth-like. And that's the best place to learn about the origin of life on Earth, maybe Mars, because the geologic record is destroyed on Earth and still there on Mars. I just heard a talk today about Venus, a seminar at the university, and that's an amazing world that we haven't explored for a long time, but it's an Earth-sized planet that took a very different evolutionary path, and we should understand why. There's two planets that we've never sent a dedicated mission to, Uranus and Neptune, so-called ice giants. We've had the Voyager flyby only. But this is a totally different class of planet, and it's a very common exoplanet. So we're studying all these exoplanets, and we haven't yet studied the best analogs here in our own solar system for those. Further out, there's the Kuiper Belt, and we visited now Pluto's system. And Pluto turned out to be very interesting with nitrogen glaciers and so forth, lots of diversity. And Charon, its biggest moon, really a double planet system, is also very interesting. So, and there's lots more large Kuiper Belt objects we haven't ever touched. So, yeah, there's a whole lot in the solar system to explore, and I like all of it.
And we get to learn about the moons of Saturn next month, so we hope that you all join us then. Let's get a big round of applause for Professor Alfred McEwen. Thank you so much.
Thank you.
You can, if you didn't get a Science Cafe schedule, we have some up here, and you can always check the website for more information. Thanks for coming, and we'll see you next month.
A question I didn't have the courage to ask. Early on, you had an acronym, STD. I didn't hear what STD, sexually transmitted disease, what came to mind, but I missed
it was SDT, Science Definition.
Okay, well, that's why I didn't ask.
Yeah, but
that was excellent. We dyslexic for that trouble with that.
Do you guys have the I didn't even spell it wrong. I don't know.
Yeah, they're all over here. Yes. Thanks for coming. Over here. They're kind of in the dark there. We used to have more lights over there. Now these lights turn on.